Everyone, welcome to the next video in our week 4 series where we'll be talking about something called the student t-distribution. So the first question is, why are we not continuing with the use of that standard normal distribution that we've spent a week and a half learning about? Well, the issue comes down to that population standard deviation. In the last video, where we learned about confidence intervals for the mean, we made the assumption that we knew the population standard deviation. If we don't know that population standard deviation, we need to estimate it using a point estimate. And the best point estimate is the sample standard deviation. The problem comes with sample size. For large samples, the sample standard deviation is a reasonable point estimate. But as your sample size gets smaller, the less reliable that point estimate becomes. To account for this variability due to sample size and the inaccuracies that it's going to produce in our confidence intervals, we use a distribution that also depends on the sample size. And that distribution is called the student t-distribution, sometimes just called the student t-distribution or just the t-distribution. In your textbook at the beginning of section 8.2, there's kind of a cool little story about how that distribution came to be. I'm not going to test you on it, but if you're curious of how this t-distribution came about and why it's in use, there's a more detailed explanation in your textbook. We're going to look at some of the properties of your t-distribution. You can see here, we have a picture, and you'll notice that there's several different curves in this graph. They are all bell-shaped, so the student t-distribution is similar to a standard normal curve. A lot of similar properties, right? We can see that it's bell-shaped. We can see that it's symmetric about 0. We can see that it approaches the x-axis, or in this case, the t-axis, but it never quite touches. We can also see that it's a probability distribution, so we know the total area under that curve is going to be 1. So a lot of similarities to what we saw with the standard normal curve. It does have a mean of 0, just like the standard normal curve. But the standard deviation is actually greater than 1. So the student t-distribution tends to be wider and flatter than the standard normal. It also depends on something called the degrees of freedom. And for single sample experiments, the degrees of freedom is the sample size minus 1. And you can see that we've got a list of degrees of freedom here. The pink is for degrees of freedom of 1, so a sample size of 2. Blue is degrees of freedom 3, so a sample size of 4. Yellow is degrees of freedom 8, so a sample size of 9. And then that green is for sample size of 21. And then you can see that darkest line, that dark blue, is the standard normal. And you'll notice that the bigger the degrees of freedom get, the closer that student t-curve gets to the standard normal. So as n gets larger, the t-curve approaches the z-curve. So for large enough samples, there is very little difference between the student t and the standard normal curve, which is why on that previous slide, we mentioned that sample size is an issue. The smaller the sample, the less reliable that point estimate for the standard deviation, the wider our interval is going to need to be to compensate. To find those t-scores, the same way we were finding z alpha over 2 scores for our confidence intervals in the last video, we're going to use table F instead of table E, and table F is going to be posted on Canvas. Or you're going to use inverse T on your calculator, TI-84. Or you're going to use GeoGebra and its inverse t distribution. those function calls work just like the inverse norm, inverse normal function call. And they're looking for similar information, except now it's that area in the tail and then the degrees of freedom. We're going to do some examples. I'm going to pull up my TI-84 really quick. And we are finding the critical t-score for the following scenarios. So for the first one, we're told that we have a sample size of 20 and we want to construct a confidence interval with a 95% confidence level. So first thing I'm going to do is I need to figure out what my alpha is. So I remember that I take this number, I subtract it from 1 to figure out how much area is in the tails, 0.05. And then we take that value and we cut it in half because we have two tails, not tables, sorry. And so the area in each tail is 0.025. So we're going to take that and plug that into inverse t instead of inverse norm. And you can see that's option 4 in the distribution menu. So it asks for area in the tail. And then our degrees of freedom is 20 minus 1, which is going to be 19. And so we get negative 2.09. We drop the negative sign. And typically you're going to see t-scores written to 3 places instead of 2. So I would record this as my t alpha over 2 is 2.093. So this next one I'm going to do on GeoGebra. And you can see I've gone through this process already. Our degrees of freedom is 12 minus 1, which is 11. And our alpha over 2, we subtract 90 from 100, we get 0.10. Divide it in 2, we get 0.05 in each tail. And then let me pull up GeoGebra really quick. Shrink this down a bit. So we're going to call inverse t distribution. And it wants the degrees of freedom first and then the area. And so we get negative 1.7958, so 1.796. And again, when we use those in formulas to calculate other things, we're going to drop those negative signs. I'd like you to grab the calculator of your choice and try those next two. So take a second, pause the video, and try numbers 3 and 4. And then when you come back, I'll have the solutions on the screen for you. So for number 3, our degrees of freedom is going to be 16 minus 1, which is 15. And for that confidence level, I'm going to subtract 99 from 100, I get 1%. I'm going to cut that 1%, I get 0.5%, so 0.005. And that gives me a t-score of 2.947. For the last one, n equals 18, so degrees of freedom is going to be 17. For my alpha over 2, I subtract this from 1, I get 0.5%. I cut 0.5% in half, I get 0.25%, so 0.0025. And that gives me a t-score of 3.222. So similar to finding your z-scores, similar to that alpha over 2 process, you're just using inverse t or inverse t distribution instead of inverse normal. And you need to give it the degrees of freedom. You need to tell it sample size minus 1. All right, if you have any questions, feel free to contact me or drop by office hours Tuesday and Thursday. Otherwise, I will see you in the next video.